Petros from Deeplab, who's going to be presenting virtually on Incremental Learning Framework for Large-Scale CTR Prediction.
Hello, everybody. You can hear me? Hello?
Yep, we can hear you.
Okay. So hello, my name is Petros Katsileros. I'm a senior deep learning engineer in Deeplab and Taboola.com. And thanks for being present. It's my pleasure to present your work. It's an incremental learning framework for large-scale CTR prediction, which is actually applied in Taboola's large-scale recommendation service. Regarding the outline, we will start with our product and the scale. What is the challenge, the opportunity to solve it, the actual solution, and the results. Let's start with our product. We aim to discover what's interesting and new, working together with digital properties like publishers, mobile carriers, and other digital entities. We're very engaged with our advertisers who provide us all the relevant content to be served. And of course, we aim to satisfy our users who use our services and our endpoints. Let's see some numbers. We're working with 9,000 publishers, 13,000 of advertisers, and we have 500 million of daily active users. Here you can see some exclusive partnerships with some very popular names in the publishing domain. We're employing more than 1,700 employees. Our infrastructure is quite big, 1.4 billion unique users per month, and we serve 500,000 requests per second. We collect a vast amount of data, 3 billion page views per day, which is almost to 100 terabytes in storage. Let's see what's the challenge. So in recommender systems, content is changing very fast, user intent is changing very fast, so our models need to adapt on these changes as fast as possible. And you can see here the circular dependency between users, content, and the models. What's the opportunity now? This is a typical ML cycle. We run our ETLs, we validate the output, we train our models, we validate them, and we deploy in production. So in order to keep up to date with the rapid changes in supply and demand, we want to minimize this cycle to deploy fresh models as fast as possible. And to do it, we have to process less data per each cycle, which means faster operations, faster deployments, and thus our models will be able to capture novel trends and data distribution shifts as fast as possible. There is always a but, so less data is good for faster operations, but not good for our models, so we need to somehow preserve the strong predictive ability of them. What is the solution now? Our approach is to use transfer learning and specifically combine multiple transfer learning techniques together. We will dive specifically in each one of them in the next following slides, but let's briefly analyze them here. We use warm start to transfer pre-trained weights from the past models to the new ones, and we fine-tune with only the fresh data, which minimizes the training data size per each cycle. On top of it, we add knowledge distillation. It's a method proposed by Hinton. It's actually a teacher-student setup, and with this, we regularize the models considering past knowledge. And it's very powerful to mitigate the catastrophic forgetting phenomenon on the warm-started weights. With experience replay, we guarantee that our fresh models have enough information to optimize well and be able to give us robust estimations in the production environment. So an elegant combination of these techniques gives us some very nice benefits, both from the technical and the business aspect, and we will see them in the next following slides. Let's deep dive into the transfer learning techniques. We will start with warm start. So imagine that we are moving across time within the day, and we have a source model with a vocabulary and some strong pre-trained representations. And we transfer this knowledge to the next target models as we move to the day. And in each target model, as you see, we have some extra K1 to KJ vocabulary IDs. And the actual setup is that we fine-tune everything with the fresh data. which means that we don't freeze the warm-started weights of the source model. So on top of this, we use the teacher-student setup. Similar situation here, multiple student models within the day, and we have a single teacher model to transfer knowledge to them. But let's briefly describe what we mean with transfer knowledge here. This is the objective function of a student model. The first term is the cross entropy between ground truth labels and student estimations, while the second one, scaled with parameter alpha, is the cross entropy between teacher and student estimations on student data. So it's clear from here that student models account for teacher estimations on their own data, and it's actually a regularization technique on the objective function, which prevents them to catastrophically deviate from the warm-started weights of the teacher model. With experience replay, it's the previous setup. We have the source and the teacher model, and we transfer the knowledge to the students. And the actual setup is that each student consumes the most available information up to the time that we start a new cycle. And we keep a single source and teacher model, which practically means that we don't use student models to serve as teachers for the next iterations. Let's see the actual setup, and I believe it will make things more clear. We train our source and teacher for 2 weeks on data, 14 days. You can see on the left side, and on the right, we have cycles of 6 hours. So we have 4 different student models within the day, M1 to M4. And as you see, each one is consuming the most available data up to the time that we initialize a new run. And we see here how we transfer knowledge from the past to the future. We transfer the embeddings through the warm start from the teacher to the students. And on top of it, we apply the knowledge distillation, which actually regularizes the students while optimizing with the fresh data to not forget and not deviate from the past knowledge, which has been warm started from the previous teacher model. Let's now see what is the required infra to support this setup at scale. We use Airflow to schedule all the different operations. This is a typical flow in our system. We have our data in HDFS. We run our ETLs using Spark. We train with TensorFlow, and we deploy everything in Kubernetes. So imagine this runs daily and creates our teacher models, and there is a similar pipeline which runs every 6 hours and creates our student models. So there is an intercommunication between these 2 pipelines, because during student optimization, we need to ask from a teacher model to give estimations on the student dataset and account for them during the optimization phase of the students. Of course, this is just a single pair of a teacher-student combination, but you can imagine this is happening hundreds of times in our real system, so the actual infrastructure is much bigger than what we see here. Let's go to the results now. Applying this framework in production and A/B testing this with significant traffic for a long period of time gives us some very nice business KPI lifts. On the left, we see the CTR lift considering different traffic segments and specifically analyzing new and old campaign targets and sources. And it's crucial to note here that there is significant lift in new campaigns and targets, which means that our model is very capable under the incremental framework to keep up to date with all the novel trends that are happening in the data distribution in the production environment. And this is also translated to a significant RPM lift, again, considering this under different traffic segments, but also overall, we got a positive lift through the application of the framework in the production system. And not only this, but we have 12 times faster train and deploy cycles because we minimized a lot the computational resources per each cycle because we minimized the consumption of the dataset. And it's very important for a large-scale application because we now have plenty of free resources to be used somewhere else. So to summarize things, delivering stable and high-performance production ML frameworks and pipelines is really hard. We have to guarantee for 24/7 stability, for high availability and robustness, and in general that everything is in place and as expected at any time. Fresh deployments play a crucial role in the RecSys, where both supply and demand change very fast and models need to adapt on it as fast as possible. And we show the significant benefits of doing so through the application and the testing of the proposed framework in Taboola's large-scale recommendation system. Finally, regarding the proposed framework, it combines different transfer learning techniques. With warm start, we minimize the train and deploy cycle times. And on top of it, with the teacher-student, we managed to mitigate the catastrophic forgetting phenomenon on the warm started weights by regularizing the optimization phase of the students while considering the teacher estimations on their own data. Finally, it is model and data agnostic and can be applied in scenarios where past representations are meaningful for the upcoming new models, as also data distribution shifts are small between consecutive timestamps, which is actually the case in the recommendation domain. Thank you very much.
Thanks, Petros. There's a bunch of questions in here. We'll try to get through a few of them. The most upvoted question is, any particular reason for not always using a student from the previous step as a teacher?
Okay, good question. We have tried this, but we have seen a degradation in performance of the transferring knowledge between consecutive students to perform as teachers. But the most important thing is that we want to have, as teacher, a quite big model trained in a lot of data, which takes a lot of time in order to transfer strong knowledge and strong representations to the upcoming student models. And if we want to train in a quite big data set, then our interval cycle needs to be small, which is not aligned with our desire to deploy fresh models in production as fast as possible.
Great. Next question is, how do you account for new item IDs during incremental learning? Okay. So regarding some specific features, there is a different pipeline that updates our backend system and our databases with the counters for these specific features. So in real time, the system is able to ask for the counters or the data for new items and use them during both the optimization phase and the serving phase. Next question is, how much does the residual effect of the oldest model have on the most recent model over the period of several months or even years?
Sorry, can you say again the question?
So the question is looking at what's the effect of it when looking at the residual, how much effect does a very old model have on recent models over longer time periods? Here it said months or years. I don't know if that's the time scale, whichever long-term time scales you've been looking at.
Okay. We haven't go as back as this, and with so big difference between teacher and students, because there is a strong relation in the content during the last month, for example, and we have seen this setup to play really well in our system, considering 2 or 3 weeks or even a month for the teacher, and train the student in a daily data set with the most fresh data up to the time that we are able to run a new cycle. I'm not sure if it makes sense to somehow use data from back a year,
but for sure there are features that have accumulated knowledge from many months ago. So they are part of the teacher model. So this knowledge is preserved there, and I think that it's being transferred to the students as well.
Cool. One last quick one. What metrics do you use for model drift?
Okay. For offline, we use several metrics regarding evaluation of the models on the future data, and we can do it by replicating the online scenario where you serve on the next items or whatever. So we did a lot of this kind of offline tests to measure the degradation in the performance of the model by considering the AUC or the log loss. But of course, we have run different tests online to measure the impact of not deploying models as fast as with the incremental setup.
Great. Thank you again so much, Petros. Let's give him a round of applause.
Thank you very much.